Hello and good evening to all. So in this tutorial class we will discuss about improper integrals, which is one of the important topics to be discussed on this online NPTEL platform. So we hope that you all know what is we call Riemann integral, and then knowing the concept of Riemann integral we will build up upon improper integrals. Okay, so first of all, in this section our aim is to extend the concept of integration to the following cases. So there are two types of improper integral, that is improper integral of type 1 or first kind, improper integral of second kind. So the function f(x) defined on unbounded interval a comma infinity, and f is a Riemann integrable function for all b greater than a. And the second is that the function is not defined at some points on the interval a comma b. So this type of improper integral we call them as type 1 improper integral. Please, the person who have joined, please stay with me. Okay, today I am just discussing improper integral, so please stay with me. So the function f(x) defined on unbounded interval a comma infinity, when f is Riemann integrable for all b greater than a. And the second kind of we will discuss the function that is not defined at some point on the interval a comma b. So we first consider improper integrals of first kind. Suppose that f is bounded function on a comma infinity and f is Riemann integrable for all b greater than a, then the improper integral of f on a comma infinity is defined as a to infinity f(x) dx equal to limit b tends to infinity a to b f(x) dx. If this limit exists and is finite, we say that the improper integral converges. If the limit goes to infinity or does not exist, then we say that the improper integral diverges. So what is improper integral of first kind? Suppose that you have some function f, and that function f is bounded function defined on a comma infinity, and this f is actually a Riemann integrable function for all b greater than a. Now what is your definition? The improper integral of f on a comma infinity is defined as a to infinity f(x) dx equal to limit. So what we will do, we will just substitute, instead of infinity we will take substitute b, and this limit b tends to infinity a comma b f(x) dx, we will try to determine this. and if this limit exists and is unique, we say that the improper integral actually converges. Or if the limit goes to infinity or does not exist, then we say that the improper integral diverges. So first of all, 1 to infinity 1 by x squared dx, 1 to infinity 1 by x squared dx. And so how to solve it? So what is the technique? So this is the technique, just to use the definition, and later we will learn some tricks like comparison test and all, because with just comparison test you can tell that whether the integration actually converges or not. So but since these are actually simple problems, so I think that we can actually solve this. So limit 1 tends to 1 to infinity 1 by x squared dx. So instead of infinity you put just b. So limit b tends to infinity integration 1 to b dx by x square. So this is equal to, so if you integrate 1 by x square from 1 to b, what will be your answer? Your answer will be 1 by minus 1 by b plus 1. That means 1 minus 1 by b, right? So limit b tends to infinity 1 minus 1 by b, this is equal to 1. And second is like integration 0 to infinity dx by 1 plus x square. So dx by 1 plus x square is limit b tends to infinity 0 to b dx by 1 plus x square. So limit b tends to infinity 0 to b dx by 1 plus x square. This is equal to limit b tends to infinity, and you know that this is actually arc tan x, and arc tan x means tan inverse x. So what will be your arc tan x, and what will be your limit? Your b goes to infinity, so you will get, actually from here you will get arc tan b minus arc tan 0, and arc tan 0 is actually 0, and when your b tends to infinity, your arc tan b will be pi by 2, right? Next we will discuss that is called comparison test. Suppose that you have 0 less than or equal to fx less than or equal to phi x for all x greater than or equal to a. Then what will happen? Then if fx dx converges, this fx dx, this small integral will converge if the phi x dx converges, and also this fx dx, this fx dx, that will also diverges in fx dx diverges. So here we have two things to remember. First of all, if this phi x, which is actually greater than or equal to fx, if we know that this phi x actually converges, okay. So if you have 0 less than or equal to fx less than or equal to phi x for all x greater than or equal to a, and you have this statement that integration a to infinity phi x dx converges, then integration a to infinity fx dx also converges. If, and also this large function phi x, that will also diverge if you fx also diverges. So there is this proof, and I will not discuss this proof. You can just, it's very simple, you can just look and you can understand the proof. So we have learned one theorem that is called one test that is called comparison test. By using this comparison test we can actually tell that whether a integration is convergent or not. So one is actually 1 to infinity dx by x square into 1 plus x. So you note that, and x square into 1 plus e की power x is less than 1 by x square, and 1 to infinity dx by x square converges. Okay, So you have integration 1 to infinity dx by x square into 1 plus x. So you what we get that you dx by x square into 1 plus x. Now 1 by x square into 1 plus e power x is less than 1 by x square, and hence 1 to infinity dx by x square converges, and 2 is integration 1 to infinity x cube by x plus 1 dx, and you note that x cube by x plus 1 is greater than x square by 2. How? Because this x is greater than 1 within this interval 1 to infinity. So your x cube by x plus 1 is greater than x cube by 1 plus 1, that is x cube by x cube by x plus x. So x cube plus x is x cube by 2x. So that means x cube plus by x plus 1 is actually greater than x square by 2. So this x square by 2, this is actually if you integrate over here, so you will get this limit to be infinity, x cube by 6, and then if you put just infinity, you will get this to be divergent. So from comparison test, what you can conclude, since this x square by 2 is divergent, so this integral also diverges. And here the opposite thing, here since 1 by x square into 1 plus ex, this is less than 1 by x square, and just I have proved that integration 1 to infinity dx by x square converges, so therefore your this integration also converges. Now let f be a Riemann integrable function for all b greater than a, then we say a to infinity fx dx converges absolutely if the corresponding integration of the modulus function also converges. Okay, so when this fx dx will converge absolutely, we will call this is convergent absolutely if integration a to infinity modulus of fx dx converges. So in the following we show that absolutely convergence implies convergence of improper integral. So what does it means? That if the modulus function is convergent, then the fx function is also convergent, and this is the proof. It is a very easy proof. It is not that very tough one. Okay. It is just technically what we have done, that 0 less than or equal to fx plus mod fx, this is less than 2 mod fx. Now since mod fx is convergent, so 2 mod fx is also convergent, the integral also convergent. Then this integration a to infinity fx plus modulus of fx dx, this is also comparison test converges. So a to infinity mod fx converges, therefore a to infinity fx dx equal to just addition of this term and then minus of this term. So we did nothing. That means it can be written as subtraction of two integrable functions. So therefore this a to infinity fx dx convergent. The converse of the above theorem is not true. So the converse of the above theorem is not true. How to prove it? So for example, you take the integration pi to infinity sin x by x dx. This integral does not converge absolutely. So what does it means? For example, you take the integral pi to infinity sin x by x dx. This integral does not converge absolutely. How to prove it? So this pi to infinity, you break it first like that, limit n equal to 1 to infinity n pi into n plus 1 pi by mod sin x by x dx. Now you have this x to be greater than n pi. So this integration you can write it as greater than or equal to 1 by n pi. Instead of x we have just put n pi. So instead of x we put n pi, so this will be greater than or equal to sigma n equal to 1 to infinity 1 by n pi. N pi to the upper limit is n plus 1 into pi, and then here the sin x, sin x, and then in this n pi to n plus 1 pi it is just 0 to pi sin x. Okay, how we have just in 0 to pi actually n pi to n plus 1 pi. For 0 to pi your mod sin x is actually positive, it is actually sin x. Pi to 2 pi, and then 2 pi to 3 pi. Okay, now if you integrate this sin x, what you will get? You will get to be sin x integration will give you sin x will give you minus cos x, and minus cos pi is minus cos pi is minus 1, and then there will be minus plus cos 0. Minus cos pi is equal to minus of minus 1 equal to 2, so there you will get 2 by now here. So on the other hand you just so you get 2 by pi into n equal to 1 to infinity 1 by n, so this series is actually not convergent. This series is actually a harmonic series, and harmonic series is not convergent. On the other hand, we have to use integration by parts. So limit b tends to infinity 1 to b sin x by x dx equal to limit b to infinity 1 to b 1 by x, and then d of 1 minus cos x. The sin x is 1 minus cos x. And then it becomes sorry, there would have been one bracket here. So there is one bracket 1 minus cos b by b, and plus integration 1 to b 1 minus cos x by x square dx. And now it is not that difficult to show that the limit on the right hand side exists. Okay, this is very easy. This is just you can use comparison test. This is 1 minus cos x. This 1 minus cos x is always less than 2. So this 1 minus cos x by x square is less than 2 by x square. In fact, this is actually absolutely convergent, and absolutely convergence implies conditionally convergent. Similarly, we can just use like you need to show that this integration converges, that integration 1 to infinity sin x by x cube it is easy to see that sin x by x cube is less than or equal to modulus of 1 by x cube, and integration 1 to infinity dx by x cube converges. That means this series converges absolutely, and therefore it converges conditionally. And also this integral actually convergent. Why? Because this series is actually this integral is actually convergent. Since it's absolutely convergent, you can just prove it on your own. That is, since it is absolutely convergent, you can write it as you can write it to be convergent. Now problem 2, you have integration 0 to infinity e की power minus x square into sin x by log of 1 plus x. Okay, so you have e की power minus x square sin x log of 1 plus x. So here first note that limit x tends to 0, e की power minus x square sin x by log of 1 plus x equal to 1. Therefore the integral is proper at x equals to 0. So you have to consider about so you have, since if you put 0 equal to in the denominator you put 0, you will get a singularity, right? Log of 1 plus x, log 1, and log 1 is 0. So 0 to infinity e की power minus x square sin x. Here first note that limit x tends to 0, e की power minus x square sin x by log 1 plus x equal to 1. Therefore the integral is proper at x equals to 0 for x greater than 10. Say, so modulus of fx, this is less than or equal to e की power minus x square by log of 1 plus x. This is less than e की power minus x square, less than or equal to e की power minus x. Just we have used the, what we have used? We have just used comparison test. How comparison test? That this you get less than or equal to e की power minus x. Integration 10 to infinity e की power minus x dx will be convergent. And what about, you can ask me that what about the entire integral? So in 0 the limit exists, right? So that's why integration 0 to 10, this integration will be just limit proper integral, right? Riemann integral. So only you have to, the improper part is up to 10 to infinity, and for 0 to 10 it is like just convergent ordinary Riemann integral. So then you can just determine that integration 10 to infinity e की power minus x square sin x by log 1 plus x, this is converges by comparison theorem. Similar test we know that limit comparison test. Now let fx and gx are defined and are positive for all x greater than or equal to a, and your limit extends to infinity fx by gx equal to l. Then if l is positive, then either both convergent or both divergent. If l equal to 0, then converges, fx converges if gx converges. Okay, so if l equal to 0, fx converges if gx converges, and if l equal to infinity, then your fx diverges only if gx diverges. Here for any positive value of l, the like this condition holds both sides. Here only the convergence of gx implies convergence of fx. Here only convergence of here the divergence of gx implies the divergence of fx. So there you can just prove this limit comparison test. I am not in favor of just reading the proofs, so you just go through and you can actually construct the proof on your own. So next I will discuss some more problems. 1 to infinity dx by square root of x plus 1. Now take fx is 1 by square root of x plus 1, you take gx equal to square root of 1 by square root of x. Then fx by gx, you will get it to be 1, that is actually positive. So since 1 by square root of x, this is diverges, so this integral also diverges. Integration 1 to infinity dx by 1 plus x square. Similarly, just take 1 by x square, then you will get once again 1. So by the above theorem, 1 to infinity fx dx, this is convergence. x by cos hyperbolic x, cos hyperbolic x, the in exponential term this cos hyperbolic x means integration 0 to infinity x by cos hyperbolic x dx and cos hyperbolic x is e to the power x plus e to the power minus x divided by 2. So this is order of x e to the power minus x. So you choose gx as x e to the power minus x, the limit fx by gx will be 2 and integration 0 to infinity gx will converge because you have chosen x e to the power minus x and this is actually converged just in the interval 0 to infinity. Now we have improper integrals of second kind. This is also another topic, that improper integrals of second kind. Oh, sorry. Let fx be defined on a to c and f is r a c minus epsilon for all epsilon greater than 0. Then we define integration a to c fx dx, limit epsilon tends to 0, a to c minus epsilon fx dx. Then a to b fx dx is said to converge if the limit exists and is finite. Otherwise we say improper integral a comma b fx dx diverges. For example, dx by square root of x, where you have dx by square root of x. So where you have problem on the lower limit 0 itself. So you can have problem at the lower limit, you can have problem in the upper limit. If you have problem in between, you just break the integral into two parts. Okay, so dx by square root of x minus I have some more problems which I will discuss. Okay, and I will also upload the notes, so there is no issue regarding the notes and all. So limit epsilon tends to 0, epsilon to 1, dx by square root of x. This is just 2 square root of x, and 2 square root of x, if you just take limit epsilon tends to 0, it will be 2 into 1 minus square root of epsilon and it will be just 2. So that means this integral converges. This is actually the case. If you have finitely many discontinuities, then you just break it in terms. Okay. Now here also comparison and limit comparison tests can be proved with similar arguments. The comparison if you have 0 less than or equal to 5x less than or equal to fx and they have discontinuities, and then if fx dx is convergent, then phi x dx will also converge, and if phi x dx diverges, then fx dx will also diverge. You just read the theory, just information, just you read the information. I have many more problems, we will discuss those problems. Okay, next also same thing, limit comparison also same, that you have fx gx to be continuous and AC, and you have singularity in C. Then you take the in the limit. The rest of the part is just as simple as it get. So if L is positive, then they will converge or diverge together. If L is 0, then if gx dx converges, then fx dx converges. If L equal to infinity, then gx dx diverges, then a to c fx dx diverges. So you just read the limit comparison test theorem. I have many problems. I will discuss those problems, and you just read the statement of the limit comparison test. Okay, So test the convergence of the integral integration 0 to 1 e की power square root of x minus 1 by x dx. So you let fx equal to e की power square root of x minus 1 by x and gx equal to square root of x. Then by Taylor's theorem or by L'Hopital's rule, you can write it as limit x tends to 0 fx by gx equal to limit x tends to 0 square root of x e की power square root of x minus 1 by x equal to limit, there will be 1 0 sorry so this will be x tends to 0 square root of x into square root of x plus order of x by x, you will get 1. So therefore fx is integrable. I'm just giving 2 to 3 minutes, you just carefully look what I have constructed in this proof. You need to test the convergence of the integration 0 to infinity. I hope that this up to this part you are clear to these things. So this is save save. Okay, so next so tutorial class improper integral for advanced calculus for engineers, and I am your TA Sankonarayan Chattopadhyay. So there are many problems I have already given here, such as this problem, and I think we have already discussed such problems. Like this is like, and these are only for your practical practice purpose. There are some simple problems, then some good problems like dx by x if it converges. Then what some good results, ln sin x dx equal to pi by 2 into ln half. Then this problem to integration 0 to infinity ln x plus 1 by x dx by 1 plus x square. This is called comparison integral. This is comparison integral 2. Some test based upon these things. This is converges for p greater than or equal to 0 and diverges for sorry, there will be no, that will be converges for p greater than 0 only. Okay, that is one typo here. this is convergent for p greater than or equal to 0, and this is convergent for p greater than 0 and diverges when p is less than or equal to 0. This is also called mu integral. Integration a to infinity dx by x की power mu. This is convergent if mu greater than 1, and this is divergent for mu less than or equal to 1. There are many problems such as use the comparison integrals to test the convergence of the following. Okay. These problems you can easily try. Then there are some problems on mu test. Okay, some problems on mu test for type 2, then tests for convergence. Okay, and there are also many problems here, question problems continued. Then you have to apply Dirichlet test. Dirichlet test is also one of the important test in this purpose, and then I will move to some solved problems. So check the convergence of the improper integral 0 to 3 dx by x minus 1. What is the solution? Dx by x minus 1 equal to 0 to 1 dx by x minus 1, 1 to 3 dx by x minus 1. So since it has problem in only 1, so we have broken it into 1 and 1, and then just write it as epsilon 1 to tends to 0, and this is 1 plus delta to 3, and if you just integrate it, you will get this type of indeterminate form, the infinity minus infinity. So as this limit does not exist, thus you get that these to be divergent. Next, for what values of p does the integral convergence, and what is the value I 1 to infinity dx by x to the power p? You instead of, okay, this will be m. Okay, this is not m, this will be m tends to infinity. As m tends to infinity, 1 to m dx by x to the power p, limit m tends to infinity, x to the power minus p plus 1 minus p plus 1, 1 to m. You just put 1 and m, then just use m tends to infinity, so that will actually converge only if p is greater than 1. So what there will be two cases. So what will be, thus we get for p greater than 1, we'll get it to be 1 my p minus 1, and for p less than 1 this will be this, and so this is only convergent for p greater than 1, and it is divergent for p less than or equal to 1. Next problem is, let a less than b and b less than 1. Does the improper integral converge? The answer is yes. Just everything is similar. This has only problem in b part, the upper limit b. So what you will have to do, you will just limit epsilon tends to 0 b minus epsilon dx by b minus x to the power p, limit epsilon tends to 0 a b minus epsilon. You just integrate it, and if you integrate it, this is a to b minus epsilon, and you put the limits a to b minus epsilon, then this will be only 0 only when this minus p plus 1 will be greater than 0. Minus p plus 1 is 0 only if minus p plus 1 is greater than 0, that means p get less than 1, and as given p is less than 1, thus the improper integral converges, and you get the answer to be b minus a to the power minus p plus 1 by p minus 1. Next is you have to evaluate the improper integral 2 to infinity x plus 3 by x minus 1 into x square plus 1 dx. So what is the way out here? So you just need to break it into like partial fractions. So if you use partial fractions, you will get this x plus 3 in equal to a into x square plus 1 into bx plus c into x minus 1. You use so you take three conditions. You take x equal to, or you can just not using, you can also like match the coefficients. If you just match the coefficient, you multiply it, match the coefficients, and you can determine. Here I have just put arbitrary values 1 0 minus 1, and then we have just checked. You can also do in other ways. So now this integral can be broken up into this type of form. Then you can use integration term by term. You take integration term by term here, then you put the value 2 and m. Sorry, here there is also one typo. That will be not plus tan inverse 5. It will be tan inverse 2. This is tan inverse 2. Plus tan inverse 2, and then the answer will be just minus pi by 2 plus ln 5 plus tan inverse 2. Dx by 1 plus e की power x, very easy. 1 plus x is order of 1 plus order of e की power x, that is actually e की power minus x, that will be convergence. Cos x by x की power p, 1 by x की power p, that will be absolutely convergent if p greater than 0. It is absolutely convergent, it is divergent. So cos x by x की power p also divergence. No, sorry, 1 by x की power p, right? So that will be okay, let's check it out. This problem is very easy. Just e की power x plus 1 and just use comparison test and you can simply prove it. this problem. So this will you will get just using integration by parts. Okay, so this is convergent for p greater than 0. You can also use here limit comparison test. You can use. Question 6 is use integration direct compensated limit comparison test to check the integrals of convergence. Square root of t plus sin t, you take g dt equal to 1 by square root of t, first problem, and it is 1. So 1 by square root of t, it is divergent, convergent. So this is also convergent. Next is fx is x to the minus 2 e की power minus 1 by x, you take gx equal to 1, this is 0, and 0 to ln 2, that is actually converges, so you will get that also to converge. Limit comparison test. This is similarly fx, you have e की power x by x, you take e की power x as 1 plus x square by factorial 2 plus x cube by factorial 3, e की power x is greater than or equal to x square by factorial 2, e की power x is greater than or equal to x by factorial 2. Now this is will be infinity, so e की power x by x actually will be divergent. Next is use integration direct comparison test or limit comparison test to test the integrals for convergence. Dx by x square minus 2x, dx by square root of x की power 6 plus 1, dx by 2 plus cos x plus ln x. First dx by x square minus 2x, fx equal to x square minus 2x, and gx you take 1 by x square. Then finally use limit comparison test, limit t tends to infinity, gx by fx will be limit t tends to infinity, x square minus 2x by x square. And finally okay, that will be limit not t, that will be limit x tends to infinity. Okay, that will be limit x tends to infinity. So therefore this limit is actually convergent. 1 to infinity dx by square root of x plus 1. So then also this is actually you will get just use direct comparison test, you will given the convergence. And also dx by 2 plus cos x plus ln x, how you will prove that this is convergent? This is divergent. देखो dx 2 plus cos x plus ln x, this is greater than 2 plus cos x plus ln x is greater than 1. Okay, this will be dx by 1, and dx it will be 3 to infinity. So that is how it is actually proved. Dx by 2 plus cos x plus ln x. So I am just keeping the slide as it is, you just look after it. So thank you very much for joining the class. Thank you.